Okay, so in this video we're going to look at an example of how to calculate a confidence interval to estimate the difference in two population means. So I've got an example written out here. This is one of my favorite examples. You can probably guess why. We've looked at one of these data sets. This is the length of abalone that were measured in Mendocino County off of Point Cabrillo. And I showed you some pretty cool footage the week before spring break. And so the data set that you've seen before was the 116 abalone that were measured at a depth of 20 feet below the sea surface. And so we've got 116 measurements, the average being 17.7267 centimeters, and a standard deviation of that sample just over 3 centimeters. And we're going to compare those lengths to the lengths of 44 abalone that were measured at a 50-foot depth. And we can see that this is a little bit shorter at length on average, 16.4273 millimeters, but a standard deviation that's just a little bit bigger at 3.09 centimeters. Okay, so let's take a look at what we have and what we are going to need in order to calculate this confidence interval. So I'm going to scroll up to the formula in our red box up here. So we've got the S, the N's, the Y bars. What we need to use is, or what we need to find is the T critical value, so that way we can fully construct this confidence interval. So the degrees of freedom that we're going to use for this confidence interval, I actually calculated the not so simple approach, the Welch-Satterthwaite method, and I'm going to write that down here. This is 76 was the degrees of freedom, so I'm going to write that down. Let's use degrees of freedom 76, and I'm going to just indicate that was from the intense Welch-Satterthwaite method above. Okay, now the notation that we use with that T critical value, right, it looks like this. Degrees of freedom, alpha chopped in half. So we know what our degrees of freedom is, but what is alpha? What is this significance level? So remember, alpha is the complement to the confidence level. So since we were told we want 95% confidence, that makes alpha 0.05. So if we want to chop alpha in half, remember 0.05 is split between the two tails. That's going to be 0.025 area in each tail. So we're going to utilize the T table to find this T critical value, and I know that I need to go to the row that says 76 degrees of freedom and the column that says 0.025. So I'm going to open up our T table here. 76 degrees of freedom and the column that says 0.025. Now I'm looking at my degrees of freedoms along the rows, and I do not see a 76. But what I do see is 70 or 80. And I think we mentioned this before spring break, that we will just use the closest of the two. So 76, the closest degrees of freedom there would be 80. So we're going to use the T critical value of 1.99. I'm going to make a note here. So 1.99. And my note is that we used the closest degrees of freedom, which was 80. Okay, so now we've got all the components we need to construct this confidence interval. So I'm going to give myself a little bit more space here. I need to see the sample statistics. I think we're ready to go. So I'm going to consider my 20-foot depth as the sample number 1. Maybe I'll write number 1, and this will be my group number 2. Doesn't really matter, but it's just nice to keep things straight. So let's start with the 95% confidence interval for the difference in means between the mean length between the two depths. Sample mean number 1 is 17.7267. The sample mean from the second sample, 16.4273. I'll go ahead and put those in parentheses. I just think that's nice. So that's our point estimate for the difference in population means based on sample means. Our T critical value, 1.99, and our standard error, I'm going to need a pretty big square root symbol here. S from the first sample, 3.0448. It's S squared over N. We're going to add that to the second standard deviation squared divided by its sample size. Okay, so doing a little computation here for the difference in sample means first. That's the 17.7267 minus 16.4273. So that is the difference in sample means there. I think before I do much else, I want to estimate or get a value for our standard error, that big square rooted quantity. So I'm going to go do that first. The 3.0448 squared divided by its sample size of 116 plus 3.0974 squared divided by 44. So that is the standard error estimate there. And I'm going to need to multiply that. Can I just do multiply by 1.99? Okay, so I'm going to write some of that down before I get ahead of myself here. So back to our screen. The difference in sample means 1.2994 plus or minus. I'm going to keep the T critical for just a moment and write down the standard error, which was 0.5459, just about, just to show my work in its entirety here. Once I multiplied the standard error by the T critical, that nearly doubled that value. So the margin of error here was 1.0863. Okay, so I can now take my point estimate and add and subtract the margin of error here. So I'll bring up my calculator again. So 1.2994 minus that margin of error. And while I'm at it, I'll go ahead and do the upper bound. So I'm going to rewrite these values here. In interval notation, 0.213 roughly, comma, 2.385 centimeters. So that is our solution, and we will discuss what that means right now. So what we would say is that we are 95% confident that the difference in population mean length, mean abalone length, I should say, at the two depths is between 0.213 centimeters and 2.385 centimeters. So what does this imply about the two population means, right? We've got the population mean length at the 20-foot depth, and we've got the population mean length at the 50-foot depth. So notice that in this confidence interval, this is sort of like a range of values. And both of those bounds, the lower bound and the upper bound, they are both positive, right? So 0 is not contained in those two bounds. So I'm going to go back to my pen here. So let's notice that 0 is not contained. 0 is not contained within this confidence interval. Why am I making a big deal about the number 0? Because this is an interval, a confidence interval, for a difference, right? A subtraction. If two values are subtracted and you get a 0 as the result, then the two values that you started out with must have been the same, right? 10 minus 10 is a 0. 5 minus 5 is a 0. Since this confidence interval does not contain 0, this provides evidence that the population mean length in the first population, that's the 20-foot depth, is larger than the population mean length at the 50-foot depth by at least 0.213 centimeters and up to 2.385 centimeters. So let's take a look at a completely different example in which we can just hypothesize what the implications would be for different confidence intervals. So what if the confidence interval for a difference in two population means came out to be, let's do, for our first example, I'm just making up numbers here. Let's do -7, 12. Well, because this confidence interval contains 0, right? It starts with a negative and ends with a positive, so somewhere in there it is a 0. That implies that the difference in means could be 0, i.e. no difference. We would say no significant difference between population mean 1 and population mean 2. Again, to contrast, let's look at another scenario here. Second bullet point, let's look at what if the confidence interval was, I don't know, -66 to -14. So these are two negative numbers. So does that contain 0 in that interval? No, no 0. No 0. So what are the implications there? Well, that means that there is a significant difference between the two population means, or there's evidence for a significant difference. I didn't finish my quotes over here. So we would say that there's evidence that, well, which one would be bigger, right? Because there's no 0 in that interval, right? There's evidence that they are not the same. So which one's bigger? Because these are both negative values, that must mean that the value that was subtracted from the first value must have been larger. So that indicates evidence that the second population mean is bigger than the first population mean. Now this doesn't prove this is evidence that supports this claim. So this is how we calculate the confidence interval for a difference in two means and a brief interpretation for the result we get.